Hello, everyone. Welcome to AI Confluence, Day 2, Session 1. My name is Milad Amazon Khani. I'm a research scientist at Phi Labs, and the topic of this presentation is AI first predictive digital twins for engineering use cases. Before I start, I want to take a moment to acknowledge all the collaborators in this work. This has been a team effort, and I appreciate all their contributions. So I'll start with some discussions on advanced AI targets in engineering design. Then I'll talk about engineering workflows and industrial digitization. Then I'll walk you through the few tools that we developed under autonomous engineering LLMs. I'll discuss future research avenues, and then I'll finish with a Q&A session. So, Quantify's approach towards AI first engineering design is built on three main pillars. Um, Advanced AI surrogate models, where we have fast and physically consistent models with low compute costs. We have engineering workflows. These essentially empowers engineers to build and simulate realistic digital twins of factories. And we have autonomous engineering LLMs. These are frameworks that automates these design engineering tasks, such as modeling, optimization, and control of complex engineering systems. Now, let's go through each of these elements one by one. Starting with advanced AI surrogates. As you know, physics-based simulations are essential in design and optimization tasks. Engineers rely on these tools for testing, refining, and optimizing engineering systems before even building anything. And they have a lot of applications from, as you can see on the right-hand side, from aerospace and automotive to uh, computational chemistry and robotics. Uh, for example, at Boeing, engineers would use these tools to optimize the aircraft wing, or in automotive companies like GM, Ford, and Tesla simulate crash scenarios to improve the safety of their vehicles. The problem with these tools is that they are quite time-consuming and computationally intensive, and this actually hinders rapid decision making. And why does it matter? When we want to explore the very large design space, essentially this becomes very slow. At the same time, it limits the factory's responsiveness to changes in the market. And of course, when we want to scale to larger, more complex problems, these simulations become slower and slower. So our solution to this limitation is neural solvers. These are very advanced AI models, and they are 10 to 100 times faster in inference comparing to physics-based simulations, while maintaining very accurate performance within 1% of error to conventional models. They have zero-shot generalization capability, meaning they are very accurate at any resolutions, which is, again, this is a very important factor when it comes to engineering design. And they accelerate the design cycles from weeks to hours or to even minutes. So at Quantify, we have built multiple in-house AI surrogate models, and in this presentation, we will cover two of them. First, XPython, or our physics-informed neural operator, and as the name suggests, these models are based on physical equations and governing laws that describe engineering systems. So these models, for training, they don't need any training data. So data collection, as you know, it's a very difficult task for engineering and manufacturing. And the advantage of these models is that they can be trained without having access to real-world data sets. The second model, GITA, or a grapheme for transformer models, takes a different approach. The idea here is that we develop a data-driven model which is capable of modeling and learning very complex geometries, and that is something very common in real world, dealing with engineering system with a very complex and intricate geometries. Now, we will go through each of these models in details, but before that, I just want to mention that we were fortunate enough to present both of our works, both of these models at the ICML workshops. Now, why do we need physics-informed AI? When we look at conventional ML models, they often struggle to generalize to unseen geometries, engineering settings, or resolutions, meaning that they need to be fine-tuned or retrained from scratch if the setup or the settings of the engineering um, uh, platform has changed. Um, on the other hand, when we look at physics-informed model, specifically physics-informed neural operators, these are fully data agnostic models, meaning we can essentially train these models on a large range of geometries, settings, and resolutions. And this gives us the adaptability that we lack in conventional ML models. Aside from that, these models provide zero-shot super resolution, so we can predict high accuracy predictions at any resolution. And they are differentiable, meaning once they are trained, we can use them directly using gradient-based optimization approaches to optimize the engineering system without relying on other optimization approaches, such as generative algorithms. What's the business impact? It's clear. So we are having access to fast and physically consistent inference models with very low compute cost. And these models enhances adaptability, meaning that factories can now look at very diverse design options without the need for retraining or updating their models. And of course, we can have accelerated design optimization using these workflows. So at the bottom, you can see our physics-informed neural operator architecture, and on the right-hand side, we are showcasing the two different approaches we can train these models. So the top one is the conventional approaches that I highlighted its limitation. This is data-driven, very similar to neural networks laws that we are familiar with. At the bottom, you can see physics-informed laws terms. So you can see each terms describes one aspects of the physics that describes the real world system. This can be heat equation, fluid mechanics. All those known equations can be integrated as part of the training of the model using these uh, um, specific loss functions. Now, let's look at one case study that we have implemented and use our neural operators, physics-informed neural operators, and that is designing defect-free array space composites. Composites are very uh, important materials in our space due to their exceptional mechanical properties. The problem with these materials is that they are very sensitive in manufacturing. So a little deviation from the optimal manufacturing setting, and they can develop defects such as voids and delaminations. So generally, these materials are manufactured within these very big industrial autoclaves that apply heat and pressure over a long range of time. And then engineers, you can see actually you can see a 2D schematic of these autoclaves where the composite part sits on a tool, and then heat and pressure is applied to these materials. So design engineers typically rely on physics-based simulations, very intensive and time-consuming physics-based simulation to predict the behavior of the composite material given a specific manufacturing setting. So engineers have some control over this process. They can set up the air temperature profile within the autoclave, heat transfer coefficients, material properties, and the geometry of the components. And based on that, they try to find the optimal setting for a specific manufacturing process. The problem is because these physics-based simulations are very slow, the optimization iteration becomes very time-consuming. Our idea is to replace this physics-based simulation with our physics-informed neural operator, which gives us near real-time inference and can hugely expedite the optimization process. The impact would be we can achieve optimal curing with a very fast optimization process, which leads us to fewer defects, lower cost, and safer aircrafts. Here you can see one example of when the things go wrong. Here you can see the temperature of the composite material overshoots and goes beyond the limitation, and this causes material degradations. So the goal of engineers is to find an optimal manufacturing setting which avoids these scenarios. Now, this is the custom setup of our physics-informed neural operator for this specific composites case study. On the right-hand side, you can see the improvement we've achieved compared to state-of-the-art model in terms of the training, orders of magnitude lower loss. And here is a comparison between our model's prediction versus the ground truth, which is here in this case an FE simulation. The colors showcases the temperature evolution of the composites within an autoclave during time. And you can see we match almost exactly to the ground truth. In fact, the absolute error is less than 2 degrees Celsius, which is a very small number for this case. Overall, we achieved over 46% improvement over the state of the art models. We have 20 times faster inference comparing to conventional models, and because of the differentiability of these models, we achieve 3 times speed up over other optimization approaches. Now, changing gears, so far we have been talking about relatively very simple geometries and 1D cases. But when we look at real-world case studies, we often face more complex geometries and irregular meshes. Some examples here, for example, when we want to design an optimal airfoil for an aircraft wing, or when we look at the aerodynamics of vehicles. These are all have very complex geometries. And standard ML approaches like transformer or vision models actually struggle to accurately learn these settings because they're typically designed for structural data like sequences or images. So built on these limitations, we introduced our graph-informed transformer operator. And the intuition behind this is very simple. The model has two components, graph and transformer. Why graph? Because graphs are perfect tools for modeling a very intricate and complex relational dependency in the spatial domain, which is the case for many engineering setups. And transformers, we want to leverage their expressiveness to model uh, complex and nonlinear physical systems. So at the bottom, you see the architecture of Gito. I'm not going to go through the details, but what we achieved with this architecture is we were able to outperform state-of-the-art baselines in many engineering settings, and also we were able to achieve accurate real-time prediction and generalize to unseen geometries. Again, you can see some performance comparison. You can see two case studies that we looked at. Here you can see the ground truth color shows different design variables such as pressure, velocity, and so on in the engineering systems. The prediction of our model is here. And as you can see, they match almost perfectly. And looking at the absolute error, we have a very small error exists in our prediction. Overall, we achieved 12% improvement over the state-of-the-art models, and then we were able to also include zero-shot super resolution prediction for complex geometries. Now, moving on to the second pillar, engineering workflows. Uh, so our vision is to we can redefine engineering workflows by introducing industrial digitization. And the two core elements for that is physically accurate digital twins. So these are models that enable engineers to build and simulate realistic digital twins for factories, infrastructure, and so on. And two is AI surrogate models, the models that we just discussed about, two of them. These models are AI accelerated simulations and gives us real-time modeling capabilities. So these two core elements, when they combine with NVIDIA's ecosystem, the workflow really comes alive. Here, we looked at the same case study, composites manufacturing. Our physical twin is our composites autoclave. So we want to create a digital twin of this composite autoclave. Our engine is our AI surrogate model, in this case, our physics informed neural operators that we developed and we covered in the previous slides. This model is implemented in NVIDIA Physics Nemo and is powered by NVIDIA NIM for GPU accelerated inference. And our digital twin platform is NVIDIA Omniverse. Now let's take a look at a quick demo, and I want to show you how this would look like. So here you can see a digital twin of that autoclave that we discussed. So you can see two different materials. On the top, you have the composites, the composite part that uh, we want to manufacture, and at the bottom you can see the tooling or the mold. So here, the engineer can set up the manufacturing setting of what temperature, what heat transfer coefficient, how long each parameters or how long each temperature should be inside the autoclave. All these factors can be set. And once we set up all these factors, then we call the engine, which is our PINO or physics informed neural operators. Once we do that, it takes a few seconds, and then we will have the inference. Um, and then once the inference is available, then we can in real time see how the composites evolve over time. So we look at two main variables, temperature and degree of cure of composites over time. And as you can see, uh, as the time goes on, the temperature inside the composite changes. And the engineer can visually observe this and make design choices and on how we can improve and optimize this process. So this gives the engineer a real-time visibility of what things look like inside the autoclave, given a specific design setting. Okay, moving on to autonomous engineering LLMs. So, uh, what we've observed as current applications of um, LLMs in engineering is mostly procedural co-pilots, meaning they are good with scripting, connecting CAE tools, or helping with the documentation. What's lacking is domain reasoning, meaning LLM's reasoning is not involved in design trade-offs or understanding and implementing physical principles. At the same times, we often don't see complex modeling like multi-physics, multi-scales modeling, and let's say structural, thermal, and fluid simulations not available in these implementations. And we don't see the role of LLMs and its reasoning in the design optimization. Our vision is to move towards engineering AGI, and then we built AI design engineer with the theme of cognitive automation in mind. By that we mean we want to automate reasoning in design, in interpreting requirements provided by the user, identifying the key drivers in the engineering process and optimize those, and also have the LLM to analyze and guide the simulation and all the processes. Under this theme, we want to achieve and implement three things: domain-aware reasoning, uh, orchestration, and not just approximation, meaning we just don't want to have an AI model that predict things, whereas we want to have some tools that understands and orchestrate across multiple tools and simulations. And of course, we want to have reasoning to be a part of the optimization. We want to see how we can use conversational optimization capabilities of LLMs to optimize engineering workflows. So here we would like to show you the initial iteration of our AI design engineer. It has four different components. We have domain-aware reasoning, we have multimodal input processing, intelligent orchestration, and conversational optimization. For each component, we have a dedicated agent. So starting with reasoning, we have design reasoning agents. This agent receives inputs from the engineer, from whatever the design requirement is, and then processes the input and understand the design engineer's need and generate some validated design. The point is that all of our agents are backed and grounded by scientific research and literature. So any query that comes out of these or any text that is generated by these agents is grounded by scientific literature. Um, we also have knowledge processing capabilities, so any multimodal knowledge or information that is provided by the user can be processed by this agent. So the idea here is that we process the information and make sure that the design objectives are aligned with those requirements and physical principles. Next, we have our neural solver agent. Essentially, these agents have access to multiple neural solvers, pre-trained neural solvers. For example, that our XPython or physics-informed neural operator is one of the tools that we have available. And this is essentially our fast real-time simulator. So given any design parameters by the previous agents, we can run those settings we're using our neural operators very fast and near real time and get the response quickly. Finally, we have our optimization agents. The idea here is that we have a scientifically consistent conversational optimization. We want to have the LLM to decide what would be the next iteration based on all the information and the test that has been done so far. And we will see in the demo that we can successfully optimize a manufacturing process by having only a few iteration or conversational optimization iterations without the need to connect to conventional optimization approaches such as genetic algorithms. And at the end, the goal is to get the optimal design recipe. So all these agents are connected to the user through an orchestrator. So the orchestrator is the medium between the user and these agents, and this orchestrator decides and manages how each agent should be called and activated. With that, now let's look at the demo. So the agent start by introducing itself, explaining what components it has and what it can be done. For example, it discusses that it can provide optimal fuel cycle for composites processing. And we look at multiple items that it's capable to do. For example, it can gives us accurate physics simulation using our in-house physics-informed neural operators. Then the user asks about some inputs, what type of composite material we want to optimize, what is the part geometry, what are the user's performance objectives. For example, we don't want to have the temperature of the composite to go beyond a specific range, let's say. So all those information will be provided by the user, as you can see here. And this will be passed to our first agent, requirement gathering agent, or domain reasoning agent. And then the idea here is that the agent summarize all the information that is provided by the user. And then if there's any missing information, let's say there are some physical or manufacturing settings that needs to be set and the user didn't provide that, such as, for example, the temperature inside the autoclave, these agents, based on all those literature and scientific research or papers that are provided to this user, they decide what value those variables should have. And then they also provide some reasoning, scientific reasoning on why these specific values are set. So this is an effort to have one initial iteration. So we want to have all the design variables ready so we can pass this to our neural operator to have the first run of our optimization, right? Then so you can see all this information that provided that why these specific features or values are selected. Next, we move to the next section. So here we have that multimodal knowledge processing capability that, for example, if the user have some documents about how the specs of the autoclave, they can provide it. like we see here. For example, this document provided to the agents, which discusses what's the maximum and minimum values for each specific design variable. And that agent is responsible to make sure that all the suggestions that comes from the agents are aligned with the autoclave limitations. Moving forward, once we collect all the data and then we have the initial set of design variables, we pass it to the neural PDE agents, and the role here is to call our physics-informed neural operators, run the simulation, and see what would be our objectives at the end. So when we look at the output of this agent, we will see that out of 4 performance metrics that we designed for this specific case, 3 of them are passed, 1 of them is failed. So we couldn't achieve the minimum degree of cure provided by the user. Now, this is where the optimization agent comes into the picture. The goal would be to make this fail to pass by changing our design variables. Oops. And then we will show that by going through a few iterations through our optimization agent, we will see that the agents suggest some new changes to our design variables based on the scientific literature, and that actually improves the performance of the model. And over 3 iterations, we are able to get all pass for our all objective functions. So this is one example of how the optimization agent modify things. So this is the current values for our design variables. This is the recommended values by the agents. This is the change, and each variable has its own explanation on why exactly this change is suggested, and the sources provided to the paper, the specific paper that is based for this decision. So as we go forward after a few iterations, we will see, I can show you here that we will get to, yeah, all pass, only 3 iterations. This is as opposed to thousands of iterations with conventional optimization approaches. All right, for the future research avenues, we are currently working on some exciting topics. We look at traffic forecasting. We developed a diffusion transformer operator, again, based on physics by modeling the traffic as fluid flows. We achieved accurate long-term traffic forecasting, and then we are currently working on it to expand it to high-dimensional systems. For batteries, state of the health prediction, we have developed a new transformer model for advanced time series forecasting. And on the robotics, we are actively looking at and exploring 3 topics: motion planning, imitation learning, and reinforcement learning. And by that, I thank you and looking forward to your questions.
Awesome. Thank you so much, Milad, for that interesting talk. We are running short on time, but maybe let's take one quick question. I see a couple of them in from the audience. Um, okay. How generic is the design agent that you talked about in the end? And what challenges do you see in generalizing that?
Yeah, that's a very good question. So the framework that we just showed is specifically developed for composite manufacturing cases. So all those agents are crafted specifically for the need in composites manufacturing. But we have planned to generalize this. So essentially, the idea would be to how we can have these flexible agents generated for every single manufacturing process that we want to solve. So some ideas like super agents and other topics that discussed in the first day of AIQ can be leveraged to make this framework more generic and then customized for every single manufacturing process. And we are actually working on that.
Interesting. Thank you.